Bismillahirrahmanirrahim. Okay, so things are changing day by day. That's what we are seeing. I mean, not today, always. So earlier, like mathematics started with the addition, moved to multiplication, then it made a sharp change in calculus integration. Okay, or we subtract divide, then it made a sharp change to calculus derivative or differentiation. So now till now we were talking about kind of vector calculus. Suddenly all the terms turn to abstract classes. So abstract class in the sense now vector is no more vector. It's a abstract class. Calculus, the surfaces what we see, they are no more surfaces. They are classes. So if they are classes, then what are the attributes upon which we can do the final computation? So that came as orthogonal components or independent variables. Okay. Now class vector or class calculus surface all are abstract and they have orthogonal components. So when we are doing computation, any mathematical computation on vector or in the arena of calculus or both, so rather than tweaking the higher level classes, we will tweak the orthogonal components. This is what we are seeing. So in vector dot product and vector cross product. So this is what we have seen. So if I want vector dot product of these two vectors, then rather than doing computation, this is vector A and this is vector B and there is a theta angle between them. Now I can say that magnitude of A, magnitude of B and what is the B's component along A. Okay, so magnitude of A and what is B's component along A is the dot product. So dot product of two vector when they are in same direction is the multiplication of their magnitude. So this vector B we brought in direction of A and then multiplication of magnitude. So this is computation through vector, but we don't want to. So computation through vector we don't want. We want computation through orthogonal components. So vector A has orthogonal component as A1, A2, A3 in direction of ijk and B has B1, B2, B3 in direction of ijk. Then please do the A dot B in terms of A1, A2, A3, B1, B2, B3. That is the idea. So in that case, whatever comes is acceptable to me. But there should not be A and B. It should be A1, A2, A3, B1, B2, B3. Okay. This is the new thing that we are seeing. Now, if I want cross product of two vector A and B, then cross product of two orthogonal vectors is multiplication of their magnitude. So, if I want cross product of A and B, then orthogonal component. So, B's component along perpendicular to A, whatever comes, it's a small number. Whatever it comes, then multiplication of these two is the cross product. Or if this vector is by naturally it is perpendicular to this vector, then multiplication of their magnitude, that is the rectangle area. Or if they are not perpendicular to each other, then whatever is component along, okay, so orthogonal to A, that component and this component will lead to the cross product. So this will come as area of this small rectangle or area of the parallelogram. Okay, so this is what we saw, but we don't want this. In terms of A sine theta B, we don't want. So we want cross product in the terms of the orthogonal component. So orthogonal component is A1, A2, A3, B1, B2, B3. So in terms of only A1, A2, A3, B1, B2, B3, we want the cross product. We saw it will come as determinant of a matrix. So this is the science. Now things are getting complex. Now can we use the concept of orthogonal components in calculus? That is the concept. So the the concept of orthogonal component in calculus, y equal to, there is an independent variable called x. There is an independent variable called x. There is a function over x, okay, fx. So fx equal to y equal to fx equal to function over x. So y equal to fx equal to x to the power 2. Okay. So if x is independent variable, then function over x is x square. Y equal to x square. Y is dependent variable, x is independent variable. So can I consider x being in a direction of x-axis? So we have now y as a calculus surface. Y is a calculus line equation. Surface, sorry, y is a calculus graph, or y is a line equation where y equal to x square. What is dy by dx? 2x. What if y equal to x square? Then what is dy by dx? 2x. Okay. Can I rephrase this? If y equal to x square, then what is derivative of y along x-axis? This is science of orthogonal components. Now, there are three vectors, three orthogonal components. One is along x-axis, I unit vector. One is along y-axis, that is j unit vector. One is along z-axis, that is k unit vector. If y equal to x square, I don't know where x is. X may be along I, j or k. Y equal to x square. What is differentiation of y along ix? Fortunately, x is on I-axis only. So dy by dx is nothing but differentiation of y along I-axis. How much y would differ when there is a unit change in a line y equal to x square along I-axis? Okay, if there is a line, if there is a line equation, maybe polynomial, y equal to x square, then what is the change that is seen in y when there is a change of unit, one unit change along I vector? I am not saying in x, along I vector. Now this is a coincidence that x is only on I vector. So it will come to, so actually what I want is dy by di, that is dy by di into di by dx. I and x are same, so dy by dx, 2x. What is dy by dj? What is variation of y along z-axis? There is no component of y equal to x square line along z-axis or k-axis, so 0. So dy by dy by dx is 2x. Okay. Now what is the dy by du? Variation of y along any vector u. Variation of y along vector I is dy by dx. Variation of y along any vector u. That is the question. Now, suppose that if this is x-axis, if this is x-axis, this is y-axis. This is x axis and this is y axis. Okay, if there is how much y, okay, now there is a line equation like this, x square, y equal to x square. I don't bother where the x is, but this is how it is. Now, if there is a unit variation in the sense if I take 2 points, okay, any 2 points. Now, if this point is I1 along I vector, if this point is I1, then this point is I2. Difference between I2 and I1 is delta I. Now, at I1, what is the value of y? At I2, what is the value of y? So y2 minus y1, that is delta y, by I2 minus I1, that is delta I. What is delta y by delta I? If delta I tends to 0, limit of delta I tends to 0, then it becomes delta y by delta I, dy by di. What is dy by di? Now, I vector and x is varying only along I vector. This is what the kind of two dimension. So dy by di is dy by dx. If that is the case, if y equal to x square, then it is 2x square, 2x. There is an arbitrary vector. This vector is u. This vector is I, then this vector is u. Now, this is y-axis, this is x-axis. There is a line y equal to x square. If there is along this vector, not along I vector, along any vector, if there is say one unit change, then how much unit of change is seen along y-axis? That is the question. Now, along I vector, if there is a unit change, then how much change is seen along y-axis? I vector is same as x. So, dy by dx, dy by dy, dy by di, or delta y by delta I, or y2 minus y1 by I2 minus I1 is nothing but dy by dx. I want dy by du or delta y by delta u. So, if there is, so if this is x-axis, this is y-axis, we know the variation of y against independent variable or function over independent variable x, y equal to x square. So if there is a unit change along x-axis, then there is change in y-axis at 2x. So at x equal to 0, there is no change in y. If at x equal to 1, then for unit change along x-axis when x is 1, then it is 2 in y. If x equal to 10, when x equal to 10, at 10, x equal to 10, per unit change would bring 20 unit of change in y, 2x. Now, there is a vector called u. There is a vector called u. I, u. If there is a unit change along u vector, then how much unit of change will be seen in y? What is the derivative of y along vector u? Derivative of y along vector I is 2x. What is derivative of y along vector u? Let's consider 3D. In 3D, this is x-axis, this is y-axis, this is x-axis, and this is y-axis. Okay, this is xy plane. If this is xy plane, okay, if this is xy plane, then this is vertical, this is z-axis. So z axis is vertical to the xy plane. Now we have function over x and y, where x and y are independent variables. They are orthogonal to each other. So z equal to fxy. If that is true, then z equal to x square plus y square. Means it is a paraboloid. Paraboloid means from origin it will come like a parabola. Or z square equal to 1 minus x square minus y square. Then it is a sphere. Up to you what you want. Okay. So if z equal to x square plus y square, then it is a paraboloid. From center it will become like a paraboloid. Or it will become a sphere when z square equal to 1 minus x square minus y square. Then it is a sphere where at center there is a z value. Okay. So this is the equation. Now how much z, if I say z equal to x square plus y square, then how much z would vary when there is a unit chain along x-axis? How much z would vary when there is a unit chain along y-axis? So if z equal to x square plus y square, then dz by dx is 2x, keeping y constant. Or dz by dy is 2y, keeping x constant. So per unit chain along x-axis brings 2x chain. Per unit chain along y-axis brings 2y chain in z-axis. Now this is xy plane. If this is xy plane, this is x-axis, this is y-axis, there is any vector called u. This is u, this is x. So you can visualize, right? This is x. I am rotating little bit. This is u. If I rotate more, then this is y. Y, u, and then x. Now, if there is delta u variation along u vector, then how much variation is seen in z? That is the question. What is the derivative of z along any vector u? Okay, how much, what is the derivative, what is the change that is seen in z when there is unit change along u vector? How much, what is the derivative along x-axis? Partial derivative we also call. So differentiation of z along x-axis is dz by dx. Differentiation of z along y-axis, that is dz by dy. One is 2x and one is 2y. What is dz by du? If there is a unit variation along u vector, differentiation of z or derivative of z that is seen along any vector u. Okay. So d delta z, so at any vector u, if I take 2 points, z1, sorry, u1 and u2, okay, at u1, whatever the xy is, xy will have some value at u1, right? So whatever the xy value is, we have z. Now u2, whatever the x2, y2, so x1, y1, x2, y2, whatever the u2 is, then there is a value of z. So z2, z1, z2 minus z1 divided by u2 minus u1. This is the question. What is delta z by delta u? What is z2 minus z1 divided by u2 minus u1? That is the question. I am not saying x2 minus x1, y1, y2 minus x1. z2 minus z1 divided by u2 minus u1. Delta z by delta u. If delta u tends to 0 and limit exists, then dz by du. We know dz by dx, we know dz by dy. Very nice. So what approach we considered in earlier days, okay, in the Stone Age, okay, earlier days, we saw that if we want this calculation to come in a formula, then because if I want dz by du, Then at any point AB, at any point AB, if we want this calculation to happen, then FA plus delta UX, comma, B plus delta UY minus FAB divided by delta. So that is the kind of a concept of differentiation. If we want differentiation, then what is the value at 2 points we see divided by the distance between? So FA plus delta UX means whatever the delta U component along X. So FA plus delta UX, comma B plus delta UY. So this is the U2 point. There is U2 and U1 minus FAB, that is U1, divided by delta U. So that is the typical differentiation. So FA plus delta UX, comma B plus delta UY, that is the Z2 value, and minus FAB, that is Z1 value divided by delta. So if we go with the typical calculation, and if we know A comma B, if we know A comma B, and if we know delta U means delta UX and delta V, how much is the gap we are taking on the EX, then we can calculate. There is no big deal in here. So delta Z by delta U or dZ by du, we can calculate taking 2 points along vector u. Any 2 points we can take, then we can calculate the f value at these 2 points. Means that is ideal. What is the function value at these 2 points divided by the distance? So we get dz by du at any point A and B. But question arises is that can we get in formula the way we got that dz by dx equal to 2x? It comes in a formula, not at any point. Dz by dy is 2y, it comes in a formula. Okay, then what is dz by du in a formula? If we want then we went to local linearity. Local linearity, that if we have a paraboloid z equal to x square plus y square, if it is a paraboloid, then what is the equation of a tangent at any point AB? If I know the equation of the tangent any point A and B, then through some kind of approximation, if there is a variation of delta U, means delta x and delta y in xy direction, then how much is the variation that will come in the local linearity? So for that we have separate equation called fxy equal to dz by dx x plus dz by dy y. So delta z, difference in delta z equal to dz by dx delta x plus dz by dy delta y. So we can say that if we want dz by du, then it is fx xy d delta x by delta u plus fyxy delta y by delta u. So this is what we have seen. But as we say, but later we came to chain rule. Chain rule in the sense that if you want that dz by du, then along both the components, that is dz dfxy by dx into dx by du, that is a chain rule, plus fxy dfxy by dy by du. So this is what we saw in chain rule. If u is dependent upon t, then dz by dt equal to dfxy by dx, dx by du by dt. This is chain rule. Plus dfxy by dy, dy by du by dt. That is dz by dt. If t is dependent upon some other variable m, then dz by dm is dfxy by dx, dx by du by dt, and dt by dm. This is chain rule. Plus dfxy by dy by du by dt, dt by dm. That is dz by dm. So the way we keep growing the chain rule. Now we have come to another science that is called doing all the computation through the independent variable or orthogonal component. So the area arena of local linearity equation or chain rule are gone. So we will do all calculation through orthogonal component. That is the sign. Okay, so we'll talk more on it. So that is the concept. So we'll start with the 2D. We started, and then this is surface side, that is 3D, and then we will move to the line equation purely in 3D. So that is the concept. Okay, so to beat the heat, so what we have today, okay, so it is a melon. I don't know what melon it is. Okay, it is not watermelon. I believe some honey melon or something like that. So this is melon. Okay, what it is called in Hindi, I don't know. Miss, it's not that I don't know Hindi, but I have never tried this. First time I saw. Okay, so this is melon. It is evidently available and it is very cheap. Okay, so we'll try. It's also like honey. Means it is not very sweet the way papaya is, but it has a lot of water. Okay, so I believe it is Indian fruit. If it is available near to you, then I believe it is worth trying.